We begin our final lecture in this first module, the first week of the statistical physics with Python. First, I ask you if you have any questions. Actually, before that, I want to say that I probably will simplify your homework problem a little bit because it is doable, but the first part is actually a little bit more complicated than necessary. So I will tell you later what I will remove from that problem. In principle, if you would like, you can solve it, that problem as it is, but the differentiation there will have so many terms that probably is rather more of mathematical exercise than conceptual. Idris, you wanted to ask something?
Yes. For the homework, I really didn't understand the part of any particle can be excited more than once.
Yes, so in the first problem, what I will ask you, actually, I will not ask you now to split the system into halves, and you would need only to solve the problem for the whole system, what means that the particle can be excited several times. If you read the two-level systems, you see that there the particle could excite it only one time. That means if particle 1 carries energy 1 epsilon, that's all that's the maximum energy this particle can carry. So a particle may have only two levels of energy, 0 and 1. Excited multiple times, that means that the same particle can have 2 epsilon, 3 epsilon, 4 epsilon, just as much as
okay, so just to make this thing simpler, a particle can take amount of energy, but it doesn't change. Because what did I understand from one particle can be excited more than once? In T1, for instance, it is epsilon, then in T2, it will be 3 epsilon.
It could be 3, yes, it is correct. 3 epsilon cells.
So our system is time dependent.
Well, no, these problems I did not define dynamics. You see, energy function,
Exactly.
yes, energy function, as the first lecture I tried to direct you towards the idea that the function of energy, it's just a function that can be defined in various ways, but the dynamics can be really anything. It may not be Hamiltonian dynamics, but for instance, what can be an energy in a general problem? In finances, you could, instead of energy, use cost, money cost, right? For instance, you want to go and buy some stocks or bonds to play in the stocks. Your energy is your money. Okay, and there are various forms of energy, which means you bought like stocks of Apple or bought stocks of IBM. That's just two forms of energy, so to speak. But it doesn't mean that this energy will obey Hamiltonian, will lead to Hamiltonian. In this first exercise, I will not ask you to calculate the entropy of subsystems. Okay, I will ask you to do so only for the second problem, two-level systems. The expressions are a little easier. But I will, because in Miran-Kardar, this problem of finding entropy of microcanonical ensemble for two-level systems is already solved. You can read how it is done for the two-level systems and try to solve it for multi-level system. That's the idea. But the second part of the exercise, where we split the system into halves, you will need only to do this for the second problem. Okay. I also had a question from Kyrell regarding chemical potential. Okay. So Kyrell, are you here?
Yes. Yes.
Okay. So you had a question about chemical potential. Then let's talk it through together. So first law, tell me the first law of thermodynamics.
If
no, just in mathematical form as we used to already.
dE is equal to dq minus
dq minus
dw.
Okay, dq is
Change.
no expanded in terms of.
Okay.
Mm.
dq dE is equal to dq minus pdv.
No, dq.
Yeah, dq.
In terms of entropy and temperature.
TDS, sorry.
TDS, and then we also considered two terms that can go into work is PDV and
mu dN.
dN. This is pressure, and this is chemical potential. And the problem is that in this two-level system, in this simple systems, there is no volume, right? There is only number of particles. We have no, we don't need any constraint. And so, for instance, we defined temperature, right? From this expression, we already found that temperature is, okay. Temperature was, that's, so ds over dE was 1 over t, right? Do you remember how to show it?
Yes.
So we have t, we have t from this equation. We have TdS equals dE plus mu dN, and then sorry, that should be partial derivative. Then from this you see that 1 over, okay, let's rewrite just a little simpler. ds equals dE over t plus mu t over dN. And already from this expression, you can see that ds over dE is 1 over t. So now, what is ds over dN? Carol?
Mu over t.
Yes, which means that mu equals t ds over dN. Now, do you understand how to find chemical potential in these problems of two-level systems? Yes. You just need to find expression in S that depends on n and differentiate it. Then you already also you should have found temperature for those systems. You just substitute. Is it clear?
Yes. Thank you.
Yes. Then we continue on to the next item on our list of topics. Probably today we'll try to go a little fast because it's the last lecture, and I must say that my pace wasn't very quick, as quick at least as I wanted it to be. Yes, from last time there is one thing that I wanted to correct in my derivations. I beg your pardon for that mistake, which I tried to fix ad hoc, but it is probably not very very fair mathematically to do that trick. Okay, you remember when we derived canonical ensemble for a small system? It was so we defined our, so we found our normalization function, the partition function, as the epsilon e to the minus epsilon over kt, right? So that we derived this condition from expression for the partition function of the entire system, of the super system, right? We used to call it. Epsilon. So, okay. So this was the reservoir, for instance. This was the system of interest. So what is the problem? So we obtained the expression, which was P of epsilon was e to the power minus epsilon kt divided by this integral. Okay. Do you know what? Does anyone know how in statistics this probability distribution is called? Let me ask someone explicitly.
Maxwell-Boltzmann.
No, it's almost. So I'm trying to correct it so it would be real Maxwell-Boltzmann. This is sort of, I could say, very approximate Maxwell-Boltzmann distribution, but it's not in statistical mechanics. In pure statistics, it's a family of distributions that define, okay, epsilon is anything from 0 to we can pretend that our energy, as last time I told, energy is to infinity. So this is infinite reservoir we consider. And this probability.
Poisson distribution.
No, it's Poisson distribution is related to this one. Actually, you can actually take this integral explicitly, right? The epsilon e minus epsilon over kt, and we again take e to infinity. So let's forget about e, take to infinity. What is it? Who can integrate this system? Come on, Said, maybe you can integrate since you paid so much attention to the math physics course. Said?
Yeah, I'm here.
So can you integrate from 0 to infinity this function?
Yes, it might be 1 over kbt.
Kt.
And e power minus e over k.
Epsilon kt. Epsilon,
yeah,
okay.
epsilon kt.
You forgot
from 0
something.
to
there is minus sign.
Minus, yeah.
From 0 to infinity. Right, and this is actually just so what it is at infinity. This function does what? Said?
In infinity, it's becomes 0.
0, and at 0 it becomes
0. It becomes 1 over kbt.
Okay, so minus 1 over kt. So there was 0. Okay, minus times minus kt equals 1 over kt. Okay. So the probability distribution that we were considering is this one, 1 over kt e to the power minus epsilon kt. And if we plot it of epsilon at some fixed temperature, Ivana, can you tell me how this function will look, for instance, if kt equals 1? Arbitrary units. Ivana? At 0, what is this function gives you at 0?
Is e.
Well, if kt equals 1, so this is function of epsilon, right? So we put on the axis epsilon, and I say when epsilon equals 0, this function is
goes to an stable point. When e is 0.
Yeah, p of epsilon when epsilon is 0 and kt equals 1. We fixed.
It's equal to 1 over kt multiplied times e.
No, it is 1. I don't follow what you're trying, I'm sorry, to do, but so P of epsilon equals 0, KT equals 1 is 1, right?
Oh, okay. Okay.
I don't understand what you're trying to tell me, yeah, because 1 over 1
Here.
is 1 and
Okay.
epsilon e to the power 0 is 1, okay? Okay, and then when epsilon increases, what happens with this function?
It goes to 0.
It goes to 0. Yeah. So what is the most likely state of this probability distribution?
When E is 0.
Yeah, epsilon is 0, which is ultimately a very uninteresting case. And why is that? Is because in this derivation we actually assumed that our reservoir goes to infinity, and therefore this epsilon is actually so small that it's almost 0. But if we zoom in the system, usually energy will have something like that. So if you really take a magnifier, you will see that it's not going to 1 at 0. There will be some actually equilibrium value. So what was the problem? The problem was that I should have considered immediately so when I was considering this product, I should have already substituted here HQ of P. Okay. Sorry, not here. Yeah, so what I had to do was to use here HQ of P. Okay, and therefore normalization, which I had to do, was immediately to use D over XP. No, we could use epsilon of X.
Could we just use a new page? It's getting very confusing.
Yes. So what? Yes. Okay. New page. So what we had to use was immediately this function that equals dx dp over e to the minus, okay, let's use epsilon symbol, qp over kt. That's what was due to do. So immediately, not to consider just the function of epsilon, so we were expanding the function w in terms of epsilon. This was correct, but we should use immediately microscopic representation of the system, okay? That was a mistake in my notes, which can be sort of cured with a later trick, but mathematically it's not very nice thing to do. Okay? Questions? So the derivation would be exactly the same, except the normalization condition, which I used was to integrate by epsilon, but we should have used microscopic degrees of freedom to get the Z NVT. Now, with this said, I would like, there is one more thing that I needed to do last time, and I told I would do it today.
I have a question.
Yes.
Does the partition function have to be normalized?
So partition function is the normalization constant, okay? So it is the thing that normalizes the probability distribution, okay? So and in fact, you see, so as I'm going to show today, that logarithm of Z is actually 1 over beta minus, is minus kt logarithm Z is, it will be the Helmholtz free energy. And you see, for instance, if you multiply this Z by any constant you like, I don't know, C, what it does, it leads only to a term kt C plus, so minus kt C logarithm of C, logarithm of C
Plus logarithm of nz.
Yeah. and logarithm of c plus logarithm of z. And the thing is here that what is important is that all calculations that we do in physics, A is a free energy. So it's like internal energy. We usually don't care what you call zero energy, because what you are going to do with it, you are going to take a differential of A. And so,
so it will go to zero.
Yeah, constant plays no role. That's why anything that you put, so that's why concept of probability density kernel, you can define whatever you like. You can define it E minus epsilon QP over KT, or you could multiply by any constant you like. That still would lead to an object partition function that would still be valid energy, Helmholtz energy. You do no harm by doing so. Okay. Now, with this done, one thing that I wanted to talk before I show this fact that the logarithm of partition function gives you the Helmholtz energy, I wanted to talk about averaging a little more. You see the last time in the Python exercise, I showed you how from very weird probability distribution, we started to obtain distribution that is sharply and peaked around some value of energy, okay? And there was some, so there was like some dE, okay, here I will put delta E, this is delta E, and we saw that as we increase the system size, this peak of the energy, of course, shifts, because the system can hold more energy. Energy is extensive quantity. It peaks, the peak moves to a new value when we increase the system. But with that, we also notice that the uncertainty as the system size, sorry, it was also becoming large. So yeah, it was not really that. But what was, so, but it was not becoming as large, larger as fast as the value of energy. There is a famous statistical result, central limit theorem, that states that central limit theorem is formulated for independent statistical variables, but there are some extensions of this theorem to some specific cases, and although mathematically we can prove it for very limited number of systems, usually it is accepted as a phenomenological fact that in principle many even dependent stochastic variables lead to this kind of behavior when you sum many degrees of freedom. So for instance, pi squared over 2m, when they are, this pi can be even to give you energy, these pi's, they can give you they can be correlated, dependent, and usually they are. But if correlations are not very strong, which is usually the case, the average, okay, the average with of E grows within. The average of E grows as n, okay, but the answer, let me put double angle brackets to denote the standard deviation, grows as square root of n, okay. So that the ratio of E over square root of E squared is actually decreasing as 1 over square root of n. Okay, this is a rather phenomenological fact, and there are many mathematical theories, strictly speaking, it's a subject of mathematics, that study systems in which this behavior is taken as an axiom, practically. It is a phenomenological fact that many physical systems have this kind of behavior, and in thermodynamics, we also assume that all systems that we consider have this behavior. For that reason, we expect that when there is an Avogadro number of particles or such orders of magnitude of particles, for our scales, human scales, we practically, such a distribution will already look like a delta function, okay? So it looks, it's 0, 0, 0, then peaks to infinity and again 0. If we really take like a very, a device that allows us to look in the microscope, in this, with the high resolution, what happens here, you usually see in fact something like that. So it's not going to infinity, but such at macroscopic scales to which we are used and at which thermodynamics was first studied, such uncertainty is undetectable. And therefore it's a very good approximation, sort of like Newtonian physics is approximation for special relativity. And you, if you really calculate things with relativity, you notice practically no difference. We assume that this distribution in the thermodynamic limit, so we call it thermodynamic limit. This is essentially a delta distribution, okay? Delta function, E minus average E, because since you already have calculated for delta function, sorry, E, or delta E minus E bar equals E bar, right, from 0 to infinity. This is the average energy, okay? Therefore, even thinking in ensembles, although we have demonstrated how this is actually both an average and also the most likely value, right? So it's both things at the same time. And as we already saw, thermodynamic structure, the structure of thermodynamic laws emerges in the ensembles as when we consider equilibrium state as the state of maximum probability. If we add to this statement also the thermodynamic limit, that we assume that when the system becomes large, it's the distribution of variables of interest like energy. In canonical ensemble, it's a variable, for instance, is actually thermodynamic value which we would measure corresponds to the ensemble average. So we have many systems, and when you measure energy in this system, so inside ensemble, you always get the value that is almost like distributed like delta function around E. And whatever little deviations you observe, you can attribute to measurement error or uncertainty, okay? So it's plus minus this, okay? Now, this is the ensemble picture. When we have, so ensembles is, you know, a model. It's a model which helps us to judge what is going on, how properties, statistical properties of large system give rise to thermodynamic laws. But in real systems, we usually make experiments with, you know, not with many replicas of the same experimental setup. We usually observe things in the same experiment using the same system. We take 1 cup of water and coffee and measure something inside, like temperature. We measure we can measure it for very long time, but we do it with the same system. How to understand what is going on there? So suppose we have, yeah, let me first clear the page so that I will need some space here. How we understand this? I have mentioned already early in the course what is called ergodic assumption. So we assume, so this is time, and suppose this is excess of energy. Suppose we have only two energy states. System is discrete between two energy states for some reason. And so it's now like what Idris was asking me about the homework problem. In that homework problem, there was no time, but we can actually think that some systems do evolve in time, and they usually do evolve in time. But there are we also can think in parallel, as the system below just samples various states of the respective ensemble. For instance, we are measuring the energy, and suppose it's canonical ensemble system in canonical ensemble. So this square, large square, is the whole world of this canonical ensemble, and this area, which I color now with green, is collection of microstates with energy E2. Whereas part that contains blue area has energy E1, okay? And suppose the dynamics that the system follows in time, so we don't know what is the dynamics, but we just observe in time what, measure in time energy in this system. What typically we observe is that system, for instance, starts at this point, okay? At time 0, we observe energy value E2. And then it evolves in time. For instance, at second time, it is here. And we put that at time 1, at time 1, it moved to this point, to this state, which also correspond to a microstate of the ensemble. At time 3, it moved to this state, okay, 2, sorry, okay, 0, 1, 2, 3, 1, 2. We jump to 3, and then when we jump to 3, we finally observe this fluctuation, okay? I could say, for some reason, energy quickly dropped to 3. Then it's continued to be, quickly dropped to E1, and it continued to be at value E1 for another moment. And then it went back to the value of energy E2. I hope you get the pattern over here. Just the system, for instance, moves in circles, okay? And then we make time averages. Now we can take time average. So we just observe for a very long time and delta t. So delta t was just this. Okay, let me use little delta t. Little delta t, okay. So we have delta t here. Then we observe the system for a long time, and we see that system was for a very long time in the state E2, and for a very short, brief time in the state of E1. So then we could go in these circles actually for a long time, and to find just how all those delta t's, when E delta t's, for instance, this is delta t, capital delta t, when E was equal E2. Okay, and this is delta t when E was equal E1. Okay, this is, for instance, J. This is, for instance, I. So we will observe many such delta T of some length, and then when we observe a system for a very long time, capital T, we can make following probabilities: sum over I of all delta Ti, where E equals E1, 1 over T. Okay, that and 1 over T of psi of sum over J of delta T J when E equals E2. Okay, I or J doesn't matter. What is this? We could call this a probability of finding value E1, right? It gives us actually the probabilities of finding value E1 or E2 when T goes to infinity. Okay, for a very large time, we can compose new rules of probabilities. And the ergodic assumption actually tells us that these time averages will produce exactly the same probability distribution as the respective ensemble, canonical, for instance, in this case. And therefore, in other words, what also implied by the canonical, by the ergodic assumption or ergodic hypothesis is that average value of E will be the same as, like, let's say, more mathematically sound. Do you see the screen? Or I hope the last video I showed that in my screen there was nothing that blocked the screen, but later in the recorded, registered video there were panels.
It's okay, Professor.
Oh, you see?
Yes, sir. It's okay.
Okay. Is limit of t going to infinity, well, plus infinity, of dt 0 t over t of p, sorry, of p, not of p, of e at time t. You can see that basically this integral is already resembles this part of the definition for probabilities. Okay, this is ergodic assumption. Again, you know, mathematical researchers, they often, there is a branch of research where they just try to take some system and prove that dynamics of this system is ergodic. Okay, that it generates the same probability distribution of that canonical ensemble. But usually it's the case that for anything that we really want to calculate or measure something, it is too difficult to prove rigorously mathematically this property. Therefore, we usually assume that it holds, and then we'll merely make theory, make prediction, check if the theory fits. That means that our model at least captures the phenomenology of the problem. If we find that something in our theory has failed, probably we're missing some information. For instance, if we have a flipping coin experiment and find that all coins that we tried, from all coins of, I don't know, €1 value, flip with a high probability on the heads, probably there is some law that we have not detected, and such a law could be, for instance, that these coins by design always have a bias to fall on one side. Just an example. But yeah, we usually have to assume when we have no information about or strict rigorous results about the system's dynamics that ergodic assumption holds. Do you have questions? No questions? Okay. And then in that case, what is actually in statistical physics usually understood as, for instance, internal energy of a canonical ensemble is basically the average value. So it's dx dp of e to the okay, now it's going to be E, okay. So energy of a canonical system, okay, if it's not Hamiltonian, it can be anything, but it's some function that gives us energy of a given configuration over kt divided by the partition function nvt. That's what we would call the energy of equilibrium system in canonical ensemble. And similarly, one can define various quantities. Well, in the canonical ensemble, the most interesting variable that is not fixed by the constraints is energy. If you have any questions, you can ask now, and then we can make a little break. Hello. Just someone connect the microphone and tell me what's your opinion about this.
So actually, I want to ask if, for instance, in this case, we have n particle, right? Ax. What happened in this case? We use dx and dp. That means we have only x and p. What happens if you have more than one particle?
No, excuse me. Yeah, I'm sorry if this question only came up now. This is not about one particle. This symbol I use in order not to write, something like that, and times, and then dx, adding dx1, dx2, dxn, and the same thing with dp. So this symbol, yeah, is just, you can imagine that integral sign is just a symbol, but the dx is actually understood as a vector. Okay, so it's a vector that contains all values of dxi. So it's dxi, that is dx1, along x coordinate, for instance, dx second particle, also x coordinate, so on. And then it would be dx1 y coordinate. So you can all together represent as if a whole phase space consisted of these vectors. Okay, it's like a vector in the phase space. So it only means to integrate in whole the phase space. Okay.
Okay, sir.
Okay, no other questions. Let's make a break until 5:20. Let's make 10 minutes break. Hello? Is anyone there?
Here.
Yeah.
Oh,
Yeah, I'm here.
very good. All right. Now that we very quickly introduced the idea that we need to take averages, let's just do one more thing. Recall now the Boltzmann entropy definition, right? So we have defined it as number of states in the micro canonical ensemble, right? Over n p e. Okay, you remember that?
Yes, sir.
And now, Anna, tell me, what is the probability of finding a given microstate in the canonical ensemble? Microcanonical, sorry. Anna?
Yes.
What is the probability of a given
Is-
microstate in microcanonical ensemble?
Is the integral of the delta function?
No, that's probably what you are trying to find the partition function when you need to do the integral.
Okay.
You remember a carton problem, okay? What was the
Yes.
probability of a given microstate?
1 over the number of states.
Yes. So what is the number of states?
W.
W and VE, which is the integral with delta function and factorial
Okay.
in the denominator, right? Now, let's substitute this instead of this value here, which is very difficult usually to compute, but we know how to do histograms. And so if you occasionally have a way to observe states, like for instance, as you make a molecular dynamics simulation and observe how you just put molecules, models of molecules in a box and observe how they move. Then you probably won't be able to compute this function W, but you could do histograms and find, for instance, probability sometimes if a system not too large. Anna, could you substitute what we could substitute instead of W using the P, okay? The probability of a state. Anna?
Okay, just replacing it.
Yeah, so I want to, instead of W in the formula.
In terms of the probability.
Yes.
Let me, KB, the logarithm of 1, okay, 1 over P.
Yes. Logarithm of 1 over P can be yet simplified.
It's just, yes, KB logarithm 0 minus KB.
Minus KB.
Logarithm of P.
Yes. Okay. Now, note the fact that there is a fact, right, that all probabilities are equal in the microcanonical ensemble. Therefore, I could simply write this thing also like that, minus KB sum of P of each state. Okay, this was I, okay, but let me call all this variable, just label them by mu. Sum over mu, probability of microstate mu, times logarithm of pi over mu, okay? Yeah, here we can put mu because any p mu all are equal for each mu. Who knows what this formula is called? How this formula is named? Dionesa, have you seen such formula? Okay, by the way, instead of sum is when your states are discrete, and when your states are not discrete, it is an integral. Okay, then the XDP, that would be P times logarithm P of X and P. Okay, so have you seen such formula? You don't know? How do we call this formula? Okay, seems like no one wants to come up with the name. This is called Gibbs entropy. Okay, so Gibbs, actually, by the way, very often if you read research articles, the Boltzmann entropy very often is called, is defined this way, okay? So everyone understands that Boltzmann originally introduced the number of states, but in microcanonical ensemble, it's just the logarithm of P. And a nice thing of Boltzmann entropy that you also can define not only for the most likely state, you can also define entropy for a state that is not the equilibrium state, okay? Gibbs entropy, on the other hand, it describes the whole distribution. So you see that this is a formula for that you can now, right now we used distribution of the microcanonical ensemble. So this is a case when Gibbs entropy gives you the same result as Boltzmann entropy. But in general, we could use, Gibbs actually did define entropy for any probability distribution, which you will see that this definition used a lot is in the information theory. So for Boltzmann, idea works for microcanonical ensemble, but Gibbs entropy can be defined for any probability distribution. In principle, you can also note that it is just the average is minus KB, average of logarithm P. And P in the Gibbs entropy can be really any probability distribution, okay? And now, also note that we agree that in equilibrium, we want to define our macroscopic quantities as the average of the respective ensemble. And therefore, in principle, this is what usually understood as entropy in general, okay, of a thermodynamic system. When is not specified which exactly entropy we use, usually people mean this Gibbs entropy, okay? Questions? Yeah, it's not derivation. What I have shown is just as a demonstration that Gibbs entropy is consistent with the original definition of Boltzmann. So whatever Boltzmann has originally proposed, it works and it's correct. But when we go beyond microcanonical ensemble, when we want to consider more complex systems and other ensembles, then a more sensible definition was to use Gibbs entropy. And it was also essentially defined. Gibbs just said that entropy should be measured by this quantity.
So I have a question.
Yes.
So we can find S, the entropy in the other ensembles, using the partition function.
Yes, and so entropy, yes, you can use the partition function because essentially, with partition function you will get some normalization, but yeah, you out of logarithm, right? There will be partition function here. It is kernel divided by partition function, so you will you can measure entropy. Yeah, we'll see how it works because last time I promised to show you that logarithm of partition function for the NVT ensemble minus KBT is equal the Helmholtz energy A, okay? And what is the idea of this proof? So we are proving that Helmholtz free energy, in capital letter A, equals minus KT times the logarithm of the Z being canonical partition function of NVT. We proceed as follows. First, we recall that free energy, the Helmholtz free energy, is defined as the Legendre transformation of energy, E minus Ts. I remind you that d of A is then d equal to dE minus dt and dTs minus s dt, and substituting with the substitution of the first law instead of dE, we'll find minus dV being the infinitesimal work minus s dt. Okay, and from this equation we also see that the partial derivative of the Helmholtz energy with respect to temperature is minus the entropy. All right. What we are going to prove is we are going to prove that energy is equal to Helmholtz free energy plus Ts, or using this equation, it is equal to A minus partial derivative of A with respect to T times T. If we substitute the definition of the canonical definition of the Helmholtz free energy into its partial derivative with respect to temperature, we get partial derivative of minus kT logarithm of z over dt. All right. Then from here we have minus k. Minus k we take out of the sign of the derivative, and we have logarithm of z. We are using the product rule, so t log z with respect to t is equal logarithm of z plus the derivative with respect to t of the logarithm of z multiplied by t. This equals to minus k logarithm of z, and we are substituting the definition of the canonical partition function, that is the integral over all microstates. Let me call this microstates by the letter mu. Integral is taken over the whole phase space volume of e to the power minus capital E over of mu over kt, because it was a logarithm, we have to put also z in the denominator, and so we take minus, we pick up minus when taking derivative of e to the power minus e over kt, but then this minus is going to be cancelled by the derivative of 1 over t, and therefore we have plus e of mu over kt squared. All right, let me make it a bracket, square bracket. Now this expression we eventually can expand as minus k logarithm of z plus we cancel 1t over here plus k, let's put z in the denominator over here, minus e to the power capital E of mu over kt. Yeah, we strike it out, and here E over mu over kt. Okay, this equation will need to use 2 times in our proof. All right. Now, this equation, let me call it star. First of all, star can be written as follows. Minus k logarithm of z, okay, plus k. Note that this expression over here, e to the power minus e of mu kt over z, is the probability of a microstate mu. And also, note that in this expression in the brackets is the logarithm of the probability of microstate multiplied by the partition function z. In other words, it is z times p of mu. Then we rewrite the equation star as minus k log z plus k times d mu of p of mu times logarithm. We are going now to expand the logarithm of the product as a product of logarithms. Logarithm of z plus logarithm of p of mu. Which is then equal minus k logarithm of z plus k d mu p of mu times logarithm z plus, now let me put it as follows actually, minus, and then we take bracket, open bracket, minus k, let me write it as, so we integrate it over p mu, logarithm of p mu, and then we can use the sign of average, example average of logarithm p of mu. Okay, minus sign, right? Now, because logarithm of z is a constant, we can take it out of the logarithm sign, and integral over the whole space of the probability gives us 1 because of the condition, the normalization condition of the probability densities. And for that reason, these terms exactly cancel, whereas this term in the brackets is the Gibbs entropy, as we have defined just several minutes ago. All of that will just evaluate to minus s. Hence, we have confirmed this equation. Okay. Now I'm going to erase this part that I have just written here to free some space and to leave the equation star on the whiteboard, because we'll need it once again. Now I'm going to evaluate the right hand side of this equation. Right hand side equals, I substitute for a our canonical definition of the Helmholtz free energy, minus kT log z minus t, and partial derivative with respect to temperature we have just taken. This is the equation star minus k logarithm of z plus k average of E. Let me use average because this is integral over the whole phase space of the probability times the function E, capital E of the probability, E over kt. Okay, note that Boltzmann constant can be cancelled out immediately. And when we open the brace, we get minus kt logarithm z minus plus, minus and minus give us plus, plus tk logarithm z, which cancel exactly, t times t. So because t is constant, we can take it out of the ensemble average, which regards the integration with respect to mu, and t does not depend on mu. This t will cancel with the t in the denominator, and we get plus average of mu. So this is the average of energy function of a microstate with respect to the ensemble. As earlier in the today lecture we have discussed, we associate the ensemble average of quantities that depend on the microstates with the thermodynamic quantities, and therefore this is simply the internal energy of the system E. And note that this is exactly the left-hand side of the equation that we wanted to prove. No questions? Okay. Final one, just to try this, to settle down everything what we have just seen. So in principle, we started with micro canonical ensemble, right? We considered the first law, TDS minus dV, right? And actually, we found that the most convenient quantity for describing microcanonical ensemble was actually S. So we most of the time did calculations with S. That's why it's it also can be said sometimes that entropy, no, it could be said this way, that entropy is a potential, a thermodynamic potential for microcanonical ensemble, because from this quantity we could derive entropy. We also can measure work. In your homework you will do with the chemical potential, sorry, not the work, but the chemical potential or pressure. You could find all the variables which of interest from the entropy, if you know entropy of the microcanonical ensemble. Then we have shown that by considering system to be a microcanonical ensemble, as the universe assumed to be a microcanonical ensemble, we could get from here to the canonical ensemble. Okay? And for canonical ensemble, we saw that it is most convenient. Yeah, by the way, here I forgot to say that entropy was also defined as KB logarithm of the partition function for NVE. Okay, microcanonical is also NVE. Okay, from there we can derive canonical ensemble. Okay, considering it to be in a wall that only red color is that only energy can exchange, can be exchanged between this system between this red container and the universe. Okay, and we saw that most convenient quantity, actually the most important quantity in thermodynamics. Well, we didn't work too much, but with this quantity, but it's the Helmholtz free energy. A equals E minus T of S, okay? And we saw that it is also equal minus KT logarithm of the partition function NVT, canonical NVT. Example is a gas in a container, like you want to work with hydrogen, you do experiments with hydrogen. It's a very dangerous gas which burns with a lot of energy, but you put it inside container, and which is so that the gas cannot leak outside. Container is very rigid, it cannot change its volume, but inside then whatever is inside can exchange heat with the environment. So that's an example of canonical ensemble, which is already much more useful than microcanonical ensemble, that mostly is a theoretical concept, or in computational systems we can efficiently simulate microcanonical ensemble, but canonical is what already more interesting in the context of thermodynamic studies. What else? You can actually, by very similar procedure, so to derive canonical ensemble, we were using expansion of SE minus epsilon, you remember, into the powers of, yes, over the epsilon in the Taylor series. By similar token, we could go and derive what is called a Gibbs ensemble. It is PV. So it is a Gibbs ensemble, yeah, it is a volume minus little volume, yeah, that's it. So if we do expansion of entropy in terms of epsilon and volume of this container, so this V and epsilon, that, so the container can grow, okay? What is fixed in this system is pressure and temperature. Therefore, this ensemble, it is basically NPT, okay? Yeah, because temperature replaces energy, pressure replaces volume. And that is why it's called isobaric isothermal ensemble. Yeah, that's right. There is also grand canonical ensemble. Grand canonical ensemble, and actually there is also isothermal ensemble, but sorry, isothermal is the just isobaric ensemble when there is only with P, yeah, which is grand canonical. So grand canonical, it is N, actually N, no, it is mu. So here we mu V and T. So it is the container that, so here the container we need to close actually. So it is container that can expand and contract, and here in the case of grand canonical ensemble, do you see when I write here?
Yes.
Okay. So actually can exchange heat and particles. That is the grand canonical ensemble. And the procedure is very similar to usually denoted by letter psi, Greek letter psi. The potential associated here, it is E minus Ts minus mu n. We didn't write that Gibbs ensemble. It is potential. It is E plus PV minus Ts. Okay. Grand canonical mu Vt. Yeah. And well, there are several ensembles that you can define. So, and by the way, what do you guess? How you could find Gibbs energy in the statistical sense? Who has a guess? What function would give you grand canonical when you use statistical mechanics? Gibbs free energy when you use statistical mechanics? Dionessa, do you have a guess? Dionessa?
So from here?
So when we had discussed entropy, microcanonical ensemble, we found that logarithm of Wk was entropy, and that's important quantity for microcanonical. Helmholtz energy was canonical ensemble, and we extracted Helmholtz energy by taking Kt logarithm of Z. What do you think would be for Gibbs energy? Okay, that would be minus Kt logarithm of, well, let me put some other, let me use omega, which would be the partition function for the Gibbs ensemble. And yeah, sorry, grand canonical, yeah, grand potential actually would be denoted by phi, and then beta phi, and then it's also would be equal to minus Kt logarithm of grand canonical partition function. All right. So there is a whole structure which we don't have time to explore, and you can derive by similar token as we used expansion Taylor series with epsilon, energy of the system. We derived canonical ensemble, but the same token, if you use two Taylor expansion about two variables, you can derive Gibbs ensemble or grand canonical ensemble. These are very important ensembles. Thermodynamic potentials, grand potential, Gibbs energy, Helmholtz energy, and entropy. Okay, all of them, all of these potentials can be inferred by taking proper coefficient and logarithm of the partition functions in this ensemble. So the structure is actually has a very beautiful self-similarity, so to speak. Do you have questions? No questions. All right. So just let's solve a little simple problem. Try a very simple problem so that we'll see. For instance, in biology, something inspired biology. In biology, you know, there are such things that well, maybe you know, maybe you not, you don't yet. Ion channels, okay? So many cells, like neurons, in neuroscience, it's very important thing. Ion channels, they basically allow, ion channels allow diffusion into the cell of specific ions. And for instance, there will be only calcium or sodium, other elements that can go through this ion channel.
Like the sodium potassium pumps.
Yes, the sodium potassium pumps are exactly related to, so pumps is what, yeah, what pumps it puts inside, but yeah, channels allow this diffusion, okay? This is very important for many functions of biology, and sometimes, for instance, you can define that a flow, a current of a given species, let's say calcium, okay, which goes inside is a, okay, let me put it equal number of open channels, well, some coefficient, okay, coefficient. And then if channels are very many, we can approximate channels, we can evaluate the current as some constant k. It's not Boltzmann constant, let me put other kj, times the average number of channels. So it's important sometimes to know how many channels would be open. And channels, for instance, in a very simplified way, is a molecule that can be open and can be closed, okay? And you can consider it to be a chemical reaction. So there is a chemical reaction between channel opened, between the open channel state and closed channel state. Just two states. So you can imagine that your system has just two states. Okay, it's just two states. So it's one box which can be filled, opened. Okay, it's opened or it's closed. Just two states. So there are two states of the system. The molecule, by the way, is a can be very complicated object and so on. But for instance, chemists told you that energy of closed state is E, and energy of open state is E plus some delta E. Okay, and temperature of the liquid is given to be T. Okay, how would you find, and there are in total n channels, okay? So there are n channels. N channels with two states, closed open with the open state energy E plus delta E and closed state E. What is the average value, sorry, that is number with the, so it's average with respect to probability of a channel to be open, okay? So average number of, we are calculating again, number of the approximate number of channels is actually product of many channels times the fraction of these channels that are opened, which is the probability of a channel to be open, which is just kj n times number of open channels divided by n. Okay, that is the probability for a channel to be open. So how do we find probability for a channel to be open? Who knows? Any ideas?
Combination.
Combination of what?
Combination of the number of open, of a combination of.
So we find, so consider one channel, okay?
Yes, sir.
Which has only two states, open and closed, okay? Yeah. Mm-hmm. It's like cartoon problem, but two-level system, in which system can be excited, channel open, or can be just zero energy. That's all. You have, Boris, tell me, what are the possible microstates in that system?
Two.
Huh? How many microstates? Two microstates, right? In total, we have W equals 2, the total number of microstates, okay?
Yes, sir.
Okay, so if we didn't know anything about the system, probably 1/2, right? Open and closed, we don't know. But I gave you one more constraint, is that energy of the open state is larger by a value delta E, and the temperature of the environment is T. Which ensemble would you need to use? Dionys? I know, I can see who is there.
Can you say it again?
Okay, we have a problem. We want to find a probability that a channel is open. Okay, ion channel is open, given that the channel has only two possible states. Okay, open and closed. Okay. In addition, we know that energy of open state is E plus delta E, and energy of closed state is E. The temperature of environment T. What do you think is, with Boris, we found that there are only two possible microstates, but we want to find the probability of channel to be open given this condition. Which ensemble would you use? Okay, who has ideas? Well, a question, which ensemble do you think we should use in this problem?
Here we have exchange of energy, and I think canonical ensemble would be
yes,
the case.
Yes, we fixed the temperature, right? What we know in this problem? N for one channel is 1, okay? Suppose it's right now one channel. Energy, energy is something that can vary, so it's between E, so it's a set E and E plus delta E, so it's a variable, right? So it's not fixed, and temperature. So it is like a canonical ensemble, okay?
So,
yes?
This minus or plus?
Where? E plus delta E. Huh?
Finally, in this case, what is the total energy?
Again, energy, as Idris told, can be different. So energy of the channel can change. So energy can have energy E or E plus delta E. The energy can change, but only assume discrete values, just two. Okay? So there is no constraint value, right? And Idris told that because energy can be exchanged, and I also hinted temperature is fixed, the good thing to use canonical ensemble. So what is the probability of a given state for a canonical ensemble? Who has ideas? Okay, what it is proportional to, okay? Probability of open state should be proportional to something that depends on energy and temperature. What is it?
The exponential minus E over K.
E over K. Yeah, but E of open channel is what?
Is E.
Oh, sorry. Open channel is E plus delta E, okay? Open channel is E plus delta E. Then is minus E plus delta E
Over K.
over K, that's it?
KT.
KT, okay? Now, what do we need to do to normalize this probability? Sorry, let's consider probability of closed state, okay? What is it? Closed?
Minus E over K.
KT, okay. Now, to normalize this, I said it's only proportionality. So when we sum P naught plus PC, there are no other states, right? It should sum up to 1. So how do we normalize this? Probabilities. Kyrell?
We have to multiply the or divide by.
Okay, Haya, could you give me an idea how to normalize probability P naught and PC?
Partition function.
Well, okay, partition function, Z. What is partition function?
Okay. Integral.
In this
Huh?
case,
What? So what is
say integral?
integral? Okay. Integral with respect to which variable?
E.
Anna. Okay, Anna.
E, somewhere answer.
Yes, Anna, proceed. Integral with
the
respect
integral.
to,
E.
okay, the E from which, from where to where?
0
Okay,
To delta E.
to E.
to E. So like E, so this is X is E, this is 0, and then we need to multiply all these levels, even if we know that the states of the system are only E, oh sorry, E and E plus delta E. Okay, there are only two states, but you suggest me to integrate over this interval. What's wrong? It's a
E plus delta
from
E.
A to E plus delta E.
E plus delta E.
no. So let me give you, we have discrete problems. So we don't have a spec, we don't have energy in values, we don't have energy delta E in the system. There is no such state, right? There are only two states, E and E plus delta E. Anna?
If it's discrete, shouldn't it be summation?
Summation.
Yes.
So it is summation. It is summation, let's say, over state I, where I is either open or closed. Okay, of what, Dionessa?
Wait.
Of what?
Of the channels.
Yeah, probabilities of the states of the channels, which is what?
So E. Oh, okay. P. Oh, P sub O plus
Okay,
P sub C.
O plus P of C, and this is what?
So it's the E negative E plus del E over KP.
And?
Plus, so it's just, sorry, it's just E negative del E over KP.
Okay, so this is the partition function, this ensemble, okay? So how do we get probability? So we need to divide this. So we need to divide this over Z, okay? And let's put another page. So then probability of for something to be open, we actually want this, not the other case, was what? Remind me, someone.
E raised to negative E plus delta E,
E
over
plus
KP.
delta E over
KP.
KP. And what was the normalization constant?
E plus, E negative E plus del E over KP plus exponential negative E over KP.
Okay, can you simplify this function a little bit?
Yeah.
Who wants to simplify it? Idris?
Exponential.
Uh-huh.
Exponential minus E over KT. Exponential delta E over
It's
KT.
Boris. Okay, delta E over KT.
Over exponential minus delta E over KT plus 1.
Okay, that's it. So you only need to measure what is the energy difference. For instance, you can take molecule and stretch it and measure how much energy you, very slowly, for instance, you stretch it Okay, I don't go into detail how to do such experiments, and measure the difference of E. And then just given the temperature, you can predict what is the probability of channel to be open. And then the number of channels that are open would be just number of total channels times the fraction of those channels that are open, which is approximately exactly the probability of a channel to be open. Okay, then you multiply it by a coefficient that gives you the current through these channels. Very simple. In fact, most of the, so this framework, when you derive it, it's a lot of integrals and so on, but in many instances, especially in discrete systems, the framework applies very easily. Okay, it's very simple to apply this framework, just like in this example. Okay. All right, our time is up. If you have any questions, please ask now. No questions. All right. Well, look, our first module has finished now, is over now. So I will expect your homeworks to arrive later, and I will update the homework a little bit today. I will send you a new assignment so that you, in the first problem with the multiply excited particles, you need only give me the expression for entropy of the microcanonical ensemble. Okay, you don't need to split the system into two halves. So only the entropy of the whole system, the super system, and temperature. As a help, there is this reading from Kardar notes. Okay, he derives the same quantities for the two-level system. Okay, so you can use Stirling approximation in a form like Meran-Kardar does it. So you have example. You just will have a different formula because in this problem we allow multiple states. Formula, I believe, should be a little more complicated, but anyway, do it. And then in the two-level systems, Meran-Kardar solves the problem. At least for entropy and temperature. So I only ask you to add the chemical potential of the whole system, and then consider the two-level system split into two halves, and consider similar quantities, but for the subsystem one. Okay?
Okay, sir.
All right, I hope this exercise, in fact, will help you to settle down. In principle, I hope you are realizing that it parallels what we have been doing in deriving canonical ensemble from microcanonical, and hopefully doing it now for yourselves, you will better understand what was the point of all these operations that we perform. Thank you for attention, and good luck for the rest of the course.
Thank you.
Thank you very much.
Thank you.
Thank you very much.
Yeah.